Today, we're diving into a real head-scratcher, a mystery that happens all the time, right in front of our eyes. We're calling it the case of the vanishing mass.
You've probably thought about this, right? When a log burns in a campfire, where does all of it go? I mean, you start with this big, heavy piece of wood and you end up with just a little bit of ash. It really feels like most of it just vanished. But did it really?
Well, the secret to this whole thing is a basic rule of the universe. And it's this: nothing is ever really lost. It just changes form. All the tiny building blocks of matter, the atoms, they're just rearranging themselves. Kind of like dancers on a dance floor, just swapping partners.
So if we want to solve this mystery, we've got to understand the rules of this cosmic shuffle. Let's dig into the unbreakable rules of chemical reactions.
Okay, here's the most important part. In a chemical reaction, no atoms are ever lost and no new ones are ever made. They just get rearranged. The best way to think about it is like a set of Legos, right? You can take apart a Lego house and use the exact same bricks to build a car. You end up with the same number of bricks you started with, just in a different shape.
All right, so now that we've got that rule in our back pocket, let's put it to the test with our first mystery. We're heading into the lab to see what's really going on.
So here's the setup. We've got a flask sitting on a super sensitive scale, and inside, we're about to mix some calcium carbonate, which is pretty much just chalk, with hydrochloric acid. We're going to keep a close eye on that scale to see what happens to the total mass once they start reacting.
So, if we follow our Lego rule, you think the answer is obvious, right? The mass should stay exactly the same, because no atoms can get out. But, is it really that simple? Let's see.
Okay, this is the moment of truth. This is where our unbreakable rule gets put to the test. If atoms are just rearranging, the number on that scale shouldn't budge, not even a little. Seems logical, but is it? And here are the results. We started at exactly 250 grams, but 10 minutes later, whoa, the mass has dropped all the way down to 207 grams. It looks like our rule is broken. Something weird is definitely happening here.
That's 43 grams. That's not just a tiny little rounding error. A huge chunk of mass has just disappeared from the flask. It really looks like our unbreakable rule just got smashed.
Okay, so we've got vanishing mass. Weird, but hang on, don't get too comfortable, because our next mystery is going to make things even stranger. What if I told you that instead of mass disappearing, it could actually appear out of thin air? For this next experiment, we're taking a little strip of magnesium metal, and we're going to burn it inside this special container called a crucible. Simple enough. We'll weigh it before we burn it, and then we'll weigh the white, ashy stuff that's left over.
Now, common sense, in our whole campfire log example, tells us that when you burn something, it gets lighter, right? Well, get ready for this, because the result here is totally baffling. The mass actually increased. The ash we were left with weighs more than the original metal strip.
So what is going on? We now have two mysteries that seem to completely defy logic. In one experiment, mass vanishes, and the next one, it just appears out of nowhere. How is any of this possible?
Well, believe it or not, the answer to both of these puzzles is actually the same. It's all explained by one single incredibly powerful scientific law. This is the key that's going to unlock the whole thing. And here it is. It's called the law of conservation of mass. And what it says is that mass can't be created or destroyed, ever. So that Lego rule we started with, it was right all along, which means our experiments must have missed something. But what?
Okay, here's the big reveal. Remember our first mystery, the one with the flask? Well, that chemical reaction created carbon dioxide gas. And since the flask was open, that gas, which has mass, by the way, just floated right out and escaped. That was our vanishing mass. And for the second mystery, the burning magnesium actually pulled invisible oxygen gas out of the air and combined with it. So the extra weight was the weight of the oxygen that got added.
So the whole secret comes down to this one idea: the type of system. Both of our experiments were what scientists call open systems, which just means stuff could get in or out. If we had run those exact same experiments, but in a totally sealed, closed system, like putting a lid on the flask, we would have seen the mass stay exactly the same. No change at all. Nothing was ever really lost, and nothing was ever gained.
And this isn't just some clever little lab trick. This law, this is one of the absolute cornerstones of all of modern chemistry. Its discovery pretty much changed everything we thought we knew.
The person we have to thank for figuring this out is a French scientist named Antoine Lavoisier. Way back in the 1770s, he was doing experiments just like our magnesium one, and he was the one who realized that the mass was increasing because some kind of gas from the air was combining with what he was burning. He actually named that gas oxygen, and that's how he established this fundamental law.
And you know what's really cool? This idea of conservation is universal. It doesn't just work for the stuff in a reaction, the mass, it also works for the energy. Energy can't be created or destroyed either. It just changes form. You know, like the chemical energy in a log becomes heat and light when it burns. The total amount of energy at the end is the same as the start. It's just another one of those unbreakable cosmic rules.
So, when you think about it, from the atoms that make up your body to the stars exploding light years away, nothing is ever really gone. The universe is just constantly shuffling around the same set of building blocks. So, the next time you see something that looks like it's appearing or